empty space is not truly empty, and the solidity of your hand is largely an illusion. James, our understanding of physics consistently reveals a reality far stranger than what our senses tell us.
That's exactly right, Lily. We often think of empty space as absolute nothingness, a perfect vacuum. But physics suggests that even the most empty regions are teeming with activity. Remove every atom from a sealed chamber, and what remains isn't silent. Fields still fill that space, twitching in tiny ways because the quantum world never sits perfectly still. For fleeting moments, energy can appear in a form that almost looks like particles, emerging and vanishing before ordinary matter can even detect them.
So nothingness has a hidden texture. It's not just a backdrop for physics, it has properties. This isn't just theory, is it? It sounds like something that has real, measurable effects.
It absolutely does. This restless vacuum helps explain real effects measured in laboratories. One example is a tiny force observed between metal plates placed extremely close together. It also impacts how atoms behave with remarkable precision. The universe isn't built on silence, it's built on fields that never completely stop moving. It's a foundational hum.
That's a profound thought, that even nothing is something. But let's turn to time. It feels like this steady, universal rhythm. Yet you're suggesting it isn't so straightforward.
Time isn't a universal rhythm at all. It actually runs slower near massive objects. A clock at Earth's surface ticks a little more slowly than an identical clock high above it. The difference is minute, but it is very real. This happens because mass changes the shape of time itself. Near a heavy object, time does not pass at quite the same pace as it does farther away. This effect becomes more pronounced near things with enormous gravity, like a black hole, where minutes for one person could correspond to much longer for someone watching from a safer distance.
It sounds like science fiction, but you say this isn't just a clever idea, it's been measured.
It's been measured with incredibly accurate atomic clocks. Raise one atomic clock above another, and the higher clock gains a tiny amount of time. This means time is part of the physical world, and it responds to gravity. Every second you experience is local to where you are in the universe.
So my experience of time isn't necessarily the same as someone else's, depending on our gravitational environment. And speaking of things that defy our everyday senses, light itself is a bit of a conundrum, isn't it?
Light is absolutely a puzzle. It behaves like both a wave and a particle, and no one has ever fully settled which one it really is. If you shine light through two narrow openings, it creates a pattern like ripples crossing on water. Yet, if you send the same light into certain detectors, it arrives in separate packets. Light doesn't fit neatly into the categories our senses prefer. Sometimes it spreads and interferes like a wave. Sometimes it strikes a surface as if it came in individual pieces, which we call photons.
It sounds like it can't decide what it is, which is counterintuitive. How can something be two things at once?
The famous double-slit experiment shows this weirdness most clearly. Even when photons are sent one at a time, the final pattern still builds up like something has explored more than one path. Physics doesn't say light is secretly one familiar thing wearing a disguise. It says our familiar categories are too small. Light reveals a deeper rule of nature where possibility itself has structure before an event becomes definite.
That's a profound rethinking of what is. And if our common sense is wrong about light, it's probably wrong about matter too. My hand, for example, feels completely solid.
It feels solid, but most of your body is empty space. Your hand feels solid because atoms push back against other atoms. Inside each atom, the central nucleus is incredibly tiny compared with the surrounding region occupied by electrons. If an atom were enlarged to the size of a stadium, its nucleus would be like a small object near the center, while the electron region would stretch far outward. This means the matter in your body isn't packed like bricks. It's more like organized charge and motion held together by forces. You can't pass through a wall because the electrons in your atoms repel the electrons in the wall. Solidity isn't caused by everything being filled in. It comes from strong enough interactions to stop objects from sliding through each other. Matter is mostly structured emptiness with powerful rules.
So my hand is mostly empty space, yet the forces involved make it feel absolutely impenetrable. That's a strange kind of solidity. But what about truly dense matter? I've heard about neutron stars.
Imagine this. A teaspoon of neutron star material would weigh billions of tons. After a massive star collapses, its core can become so compressed that protons and electrons are forced together into neutrons, packed beyond anything found on Earth. A mass greater than the Sun can fit inside a sphere about the size of a city. That level of density is almost impossible to picture. Its gravity would be so intense that ordinary material couldn't support it here. Neutron stars are laboratories made by the universe where matter is pushed to the edge of what physics can describe.
Billions of tons in a teaspoon. That's a mind-boggling amount of mass. It really underscores how extreme conditions in the universe can be. Does the universe also have fundamental limits on what's possible?
It does. The universe has a speed limit built into reality. Nothing carrying mass can outrun light in a vacuum. This isn't because our engines are too weak or our technology hasn't advanced enough. It's because speed changes the relationship between energy, time, and motion. As an object with mass moves faster, adding more energy gives less and less extra speed. To reach light speed would require an infinite amount of energy, making it unreachable for ordinary matter. Light itself travels at that limit because photons have no rest mass.
So there's no engineering workaround for this. It's a fundamental constant.
It's a boundary woven into the structure of space and time. This rule links distant galaxies to the smallest particles in a laboratory, and it also protects cause and effect. If information could move faster than light, events could be seen in impossible orders, and the logic of reality would start to break down.
That makes sense. But then, how do you explain quantum entanglement, which Einstein famously called spooky action at a distance? It sounds like particles instantly affecting each other across vast distances, which might break that speed limit.
Entanglement did trouble Einstein, precisely because it seemed to challenge the idea that distant objects need time to influence each other. When two quantum particles become entangled, their properties are described by one shared state. Separate them by a room, a continent, or far more, and a measurement of one is still connected to the other. Experiments have shown that entanglement is real, and the results are stronger than any hidden local instruction could explain. The crucial detail is that it cannot be used to send a message faster than light. The link isn't a secret radio signal racing through space. It's a sign that quantum objects don't always possess definite separate properties before measurement. It suggests nature is less divided into independent pieces than everyday experience makes it seem.
So it's not a violation of the speed limit, but a deeper connection that we don't fully grasp. It really highlights the oddity of the quantum world. What about forces? Gravity feels weak, yet it shapes galaxies.
Gravity is the weakest force, Lily, yet it shapes galaxies. A small magnet can lift a paperclip against the pull of the entire Earth. That simple moment shows how weak gravity is compared with electromagnetism. The reason gravity dominates on the largest scales is different. It always attracts ordinary matter, and it reaches across unlimited distance. Electric charges usually balance out, but gravity does not cancel that way. Every star, planet, cloud, and grain of dust adds to the pull. Across vast stretches of space, those tiny pulls collect into enormous structures.
It's a paradox, isn't it? The gentlest force in our daily lives becomes the architect of the universe when enough matter and time are involved.
It's one of the great surprises of physics. And those enormous structures sometimes include black holes, which can stretch light until it disappears completely. Light escaping from strong gravity loses energy as it climbs away. Near a black hole, this effect becomes extreme. A beam that begins as visible light can be stretched into longer wavelengths until it fades beyond what human eyes could see. At the event horizon, escape becomes impossible.
So we don't see black holes directly because even light can't get out, but we observe their effects on nearby matter.
Exactly. To a distant observer, light from falling material appears increasingly red and dim. Gas spiraling nearby can become incredibly hot and bright before crossing the point of no return. The darkness isn't emptiness in the usual sense. It's a region where gravity has bent the possible paths of light so severely that the universe cannot send a signal back out.
It's a boundary where reality itself becomes distorted. Moving from the cosmic to the personal, it's often said that we're made of star stuff, which seems to connect to this idea of universal origins.
The atoms in your body were forged inside stars. The hydrogen in you is ancient, but many heavier atoms needed stars to exist. Carbon, oxygen, calcium, and iron didn't simply appear in finished form at the beginning of the universe. They were built through nuclear reactions inside stars and through violent stellar deaths. When massive stars explode, they scatter newly made elements into space. Later, that enriched material can become part of new stars, planets, oceans, and living bodies. Your bloodstream carries iron that was once formed in a cosmic furnace. The calcium in your bones has a history older than Earth.
It makes your own body feel like a living testament to cosmic recycling. We're truly connected to the history of stars. Let's shift back to more earthly phenomena, but with a cosmic twist. How do astronauts experience weightlessness?
An object in orbit isn't floating because gravity has vanished. Earth's gravity still reaches it strongly. The trick is sideways speed. Imagine throwing a ball so fast that as it falls, the planet curves away beneath it. It never reaches the ground because its path keeps missing Earth. That is orbit. Astronauts inside share the same falling motion as their spacecraft, so nothing presses them against the floor. They drift because everything around them is falling together. This is why the phrase zero gravity can be misleading. The better idea is continuous free fall.
So they're not escaping gravity, they're just constantly falling around Earth. That changes the everyday meaning of weight too.
It does. It's the force you feel when something prevents you from falling freely along with everything around you. And speaking of space, movies always depict explosions in space with roaring sounds, but physics tells us that's impossible.
Right, sound needs a medium to travel, and space is mostly a vacuum.
Sound is a vibration passed from particle to particle through matter. In air, molecules bump into their neighbors and carry pressure waves outward. Take away the material, and there's nothing to carry the disturbance. That's why explosions in space would not roar across a vacuum the way films often suggest. A spacecraft could shake from an impact, but sound would not cross the empty gap. Space is stranger than it looks on screen. It can contain intense radiation, violent collisions, and immense energy. Yet a person outside without a medium would hear none of it.
So the dramatic silence of space is scientifically accurate. Let's bring it back to Einstein. His theories often feel abstract, but they have tangible consequences, like the sun bending starlight.
Indeed, the sun bends starlight passing near its edge, and this single observation changed physics forever. During a solar eclipse in 1919, observers measured stars appearing slightly out of place because their light had passed close to the sun. The result supported Einstein's idea that gravity bends space-time and light follows that curved path. The sun wasn't pulling on light like a thrown ball. Instead, its mass changed the geometry through which the light traveled. This effect is called gravitational lensing, and it's become a powerful tool in astronomy. Massive galaxies can bend and magnify the light of objects behind them, letting telescopes glimpse things that would otherwise be too faint or distant.
So gravity can act like a lens without glass. That's a concrete way Einstein's theory was proven. What about something seemingly simple like water? Does it hide any surprises?
Hot water can sometimes freeze faster than cold water. This surprising effect is known as the Mpemba effect, and it has puzzled scientists for decades. It doesn't happen every time, which makes it even more intriguing. Under certain conditions, warmer water can reach ice before cooler water placed in the same freezer. Several processes may be involved. Hot water can evaporate more, leaving less liquid behind. It can create different convection currents. Dissolved gases may change too, and the contact between the container and the freezer surface can matter.
It sounds like a simple phenomenon that's actually quite complex. It's not just that hot always beats cold, but that there are multiple competing mechanisms at play. And how does Einstein's work relate to something as mundane as GPS?
Your GPS works because Einstein was right, and you use his theory every time you check directions. Satellites carry clocks that must stay synchronized with clocks on Earth. Without precise timing, a navigation device couldn't calculate location accurately. The problem is that satellite clocks don't tick at exactly the same rate as clocks on the ground. Their motion affects time, and their height above Earth affects it too. Engineers correct for both using ideas from special and general relativity. If those corrections were ignored, location errors would grow quickly, and the system would become useless.
So, our everyday technology relies on physics that once sounded almost unbelievable. It's built into the very fabric of modern timing networks. And physics is also at play in something as graceful as a figure skater.
A spinning figure skater demonstrates conservation of angular momentum. When a skater pulls their arms inward, their spin rate increases. No engine suddenly turns on. The change comes from a rule of rotating motion. With less mass spread far from the center, the skater must spin faster to keep the same angular momentum. Stretch the arms outward and the rotation slows. The same principle helps explain many spinning systems, from a collapsing cloud of gas to a diver tucking during a flip. Physics often hides in ordinary movement. A graceful spin on ice becomes a visible demonstration of nature's strict accounting rules.
It connects a rink performance with the motion of planets forming around young stars. That's a beautiful demonstration of scale. What about rainbows? Do we all see the same one?
A rainbow forms because different colors bend by different amounts, and no two people ever see quite the same one. Sunlight looks white, but it contains many colors. When it enters a raindrop, it slows and bends. Inside the drop, it reflects from the back surface and bends again as it leaves. Each color changes direction by a slightly different amount, so the mixed light spreads into a band. Red appears toward the outside of the arc, while violet appears toward the inside. The rainbow isn't sitting at a fixed place in the sky like an object. It depends on the position of your eyes, the sun, and the falling rain. Someone standing beside you sees their own rainbow from a slightly different set of droplets. A rainbow is a geometry event made of sunlight and water.
So, the beauty we see is intensely personal, even though it's governed by precise physics. That's a lovely way to think about it. And speaking of extreme natural phenomena, lightning is surprisingly hot, isn't it?
Lightning is hotter than the surface of the sun, believe it or not. A lightning bolt heats the air around it to an extreme temperature in a fraction of a second. The air expands explosively, and that sudden expansion creates thunder. The flash is a powerful electrical discharge finding a path through the atmosphere. The channel can reach temperatures several times hotter than the sun's visible surface, though only for a brief moment. That heat tears molecules apart and allows air to conduct electricity. Lightning looks instant from a distance, but it's a rapid sequence of physical steps. A storm cloud becomes a huge electrical machine, and the sky becomes its circuit.
It's an immense amount of energy released in a blink. Moving to something more mundane, glass feels solid, but it has strange properties too.
Glass is a solid that still behaves strangely under stress. It feels hard, but its inner structure isn't arranged like a regular crystal. In glass, the atoms are locked into a disordered arrangement, more like a liquid whose motion has become frozen. That doesn't mean old windows flow downward over centuries. That common story is misleading. The uneven thickness in antique glass usually comes from old manufacturing methods. The real strangeness is that glass can withstand pressure in some situations, yet a tiny crack can concentrate stress so strongly that the whole piece fails suddenly. That's why a small scratch can matter.
So its solidity is deceptive, and its strength depends on hidden structure and even tiny flaws. What about magnets? They seem to exert a force without any visible connection.
Magnets work because countless electrons act like tiny spinning charges. A magnet isn't powered by a secret battery inside the metal. Its strength comes from the behavior of electrons. Electrons have a quantum property called spin, which makes them act like tiny magnetic sources. In a strong magnet, many of them line up in the same direction across regions called domains. When enough domains align, the whole object gains a north and south pole. That's why cutting a magnet in half doesn't produce a lonely north pole and a lonely south pole. Each piece becomes a smaller magnet with both poles. The familiar pull on a fridge door comes from countless quantum scale alignments working together. Magnetism feels simple in the hand, but its origin is deeply atomic.
It's a macroscopic effect of microscopic alignment. And then there are superconductors, which take this idea of electrical flow to an extreme.
Superconductors can carry electricity with no resistance at all. Once started, the current can keep going for years. In an ordinary wire, moving electrons lose energy as heat. In a superconductor, the rules change. cools certain materials enough, and electrical resistance drops to exactly nothing. The effect happens because electrons stop behaving like separate travelers fighting through a crowd. They form linked pairs that move together through the material in a coordinated quantum state. Superconductors also push magnetic fields out of their interior, which allows a small magnet to hover above them with eerie stability.
The idea of current flowing indefinitely with no energy loss is almost revolutionary. The dream, of course, is to find superconductors that work at everyday temperatures.
If that happens, power grids, medical scanners, and transport systems could change significantly. We already see this physics in action with maglev trains.
Where a train floats on invisible forces. That seems like an impressive application of these principles.
A maglev train doesn't need steel wheels gripping rails. Powerful magnetic systems lift and guide it above the track. Once it's hovering, there's far less contact friction to fight, so the ride can become smoother and faster. The train is held in place by forces you cannot see, but can measure with precision. This is physics turned into transport. The same basic idea that makes two magnets push apart can help carry hundreds of passengers at high speed.
It shows that levitation doesn't have to mean magic, but precision engineering. Speaking of things that seem to defy common sense, quantum particles can tunnel through barriers they shouldn't be able to cross.
They absolutely can. In the everyday world, a ball that lacks enough energy to climb a hill simply rolls back. A quantum particle doesn't always follow that familiar rule. When it meets a barrier, its wave-like description can extend slightly through the other side. Sometimes the particle is later found beyond the barrier, even though ordinary thinking says it never had enough energy to pass. This is called tunneling, and it's not a rare curiosity hidden in equations. It helps the sun shine, for example, because particles inside stars can get close enough to fuse more often than classical physics would allow.
So, nature sometimes treats a barrier less like a solid wall and more like a probability that can be crossed. That's astonishing. What about other common substances, like water? We touched on its freezing, but it also expands, which is quite unusual.
Water expands as it freezes, unlike almost every other substance on Earth. Most materials shrink when they cool because their molecules settle closer together. Water breaks that pattern in a way that changes the planet. As it freezes, its molecules arrange themselves into an open crystal structure. That structure takes up more room than the same molecules did as liquid water. This is why a sealed bottle can burst in a freezer and why cracks in rock can widen during winter. Over many cycles, this helps break stone into soil and shape landscapes.
It's a subtle molecular oddity with immense geological and ecological consequences. And the fact that ice floats is directly related to that, isn't it?
Yes, ice floats because its crystal structure makes it less dense, and this one small fact protects entire ecosystems. If frozen water sank, winter would be far more dangerous for life in lakes and ponds. Ice stays on top because it's less dense than liquid water. That floating layer becomes an insulating cover. Beneath it, water can remain liquid, giving fish and other organisms a place to survive until warmer conditions return. This simple detail matters on a planetary scale. A small floating cube is evidence of a molecular arrangement that helps keep parts of the living world from freezing solid.
So something as ordinary as an ice cube in a drink is a sign of a unique property essential for life. You also mentioned boiling water, but what about boiling at room temperature?
A vacuum can make water boil at room temperature. Boiling isn't only about making water hot. It happens when the pressure of water vapor can push back against the surrounding pressure. At sea level, that usually requires high heat because the air above the water presses down strongly. Lower the outside pressure enough, and the water can boil without becoming hot in the normal sense. In a vacuum chamber, room temperature water can bubble as if it were on a stove. The strange part is that boiling can then cool the remaining water because the most energetic molecules escape first. This is why pressure matters so much in cooking, weather, and space survival.
Boiling is a contest between vapor and pressure, not simply heat winning. That's a completely different way to think about it. Let's return to space, specifically our moon. It seems like a constant companion, but it's not, is it?
The moon is drifting away from Earth every year, just a little at a time. Laser measurements show that it moves farther away by a few centimeters each year. The cause is tied to tides. the moon pulls on Earth's oceans, and Earth's rotation carries those tidal bulges ahead of the moon's position. That offset gives the moon a tiny forward gravitational tug. Over time, it gains orbital energy and moves outward. Earth pays the price by spinning a little more slowly, which makes days gradually lengthen across deep time. This exchange has been happening for ages.
So the moon isn't static. It's part of a slow gravitational dance that's reshaping our planet's rotation. And the tides themselves are a direct result of gravity's uneven pull.
Tides happen because gravity pulls unevenly across Earth. The moon's gravity doesn't pull every part of Earth with the same strength. The side facing the moon feels a slightly stronger pull than Earth's center. The far side feels a slightly weaker pull. This difference stretches the oceans into tidal bulges. As Earth rotates through those bulges, coastlines experience rising and falling water. The sun also contributes, which is why tides become especially strong when the sun, Earth, and moon line up. It's a lesson that gravity doesn't only pull, it can stretch.
It's a fascinating perspective on a daily phenomenon. And speaking of planetary quirks, Venus has an astonishing rotation, doesn't it?
A day on Venus lasts longer than its year, which still sounds backwards no matter how many times you hear it. Venus takes less time to orbit the sun than it takes to rotate once on its axis. That means a Venusian year is shorter than a Venusian day, at least by the way scientists measure rotation. The planet also spins backward compared with most planets, so the sun would rise in the west and set in the east if you could stand safely on its surface. Scientists think past gravitational interactions, atmospheric effects, and ancient impacts may all have played a role. Venus shows that a planet doesn't have to behave like a familiar clockwork ball.
Two neighboring worlds can form in the same solar system and end up with completely different rhythms. And then there's Saturn, which has a wonderfully counterintuitive property related to density.
Saturn would float if you found a big enough ocean, which is one of my favorite facts to consider. Saturn is enormous, yet its average density is lower than water. That doesn't mean it has a solid surface that would bob like a beach ball. It's a giant planet made mostly of hydrogen and helium with layers that become stranger and more compressed deeper inside. Still, spread Saturn's mass across its huge volume, and it comes out lighter than an equal volume of water. This happens because the planet is mostly light gases and is puffed out to a vast size. The floating idea is impossible as a practical experiment, but it captures a startling truth.
One of the most majestic planets in the sky is, on average, astonishingly light. And speaking of gas giants, Jupiter plays a significant role in protecting Earth.
Jupiter protects Earth by attracting many wandering space rocks. The largest planet in our solar system has enormous gravity, and that gravity changes the paths of comets and asteroids. Sometimes Jupiter pulls dangerous objects away from the inner solar system. Sometimes it captures them, breaks them apart, or sends them into new orbits. The story isn't perfectly simple because Jupiter can also redirect objects inward under some conditions, but its overall influence on the solar system is massive. It acts like a gravitational gatekeeper, constantly altering the traffic of smaller bodies.
So Earth doesn't move through space alone. It shares a system shaped by this huge planetary guardian. What about our own star, the Sun? It's constantly doing something quite subtle but profound.
The sun loses mass every second by shining, which means it's quietly disappearing while it keeps you warm. Sunlight isn't free. It carries energy away from the sun, and energy has mass. Deep in the solar core, nuclear fusion turns hydrogen into helium. A small amount of mass becomes energy during that process, and the energy eventually escapes as light and other radiation. Because of this, the sun becomes lighter every moment. The amount is enormous by human standards, yet tiny compared with the sun's total mass. It can shine for billions of years because it began with such a vast supply of hydrogen. The star is spending itself to keep glowing.
So every patch of sunlight on my skin is part of the sun's slow transformation. And that sunlight has a hidden time story too, beyond the 8 minutes it takes to reach Earth.
Sunlight takes several minutes to reach your skin, but its story starts much earlier. Energy created in the core doesn't simply fly straight out. It can be absorbed and re-emitted many times as it works through the dense inner layers. By the time sunlight leaves the visible surface, it's ready for the quick trip across space. This gives daylight a hidden time story. The warmth on your face began as nuclear energy deep inside a star, escaped through a crowded interior, then raced across millions of kilometers to arrive here. Sunlight feels immediate, but it's never truly instant.
Every beam is a message from the recent past. And just as stars create elements, they also have extreme endpoints. Some stars are so dense that atoms collapse inward completely.
In ordinary matter, atoms keep their structure because electrons occupy space around nuclei. But in the crushed remains of certain massive stars, gravity becomes strong enough to overwhelm that arrangement. Electrons and protons are forced together, creating neutrons and releasing ghostly particles called neutrinos. The star's core becomes packed with matter in a form unlike anything on Earth. This collapse can happen during a supernova. The result may be a neutron star where normal atomic structure no longer survives. It shows that atoms aren't indestructible little building blocks under all conditions. Put enough mass in one place, and even the architecture of matter can be forced to give way.
The architecture of matter itself gives way, and some of those collapsed stars become pulsars, which are remarkably precise.
A pulsar is a rapidly rotating neutron star that sends beams of radiation into space. If one of those beams sweeps across Earth, radio telescopes detect regular pulses almost like a cosmic lighthouse. The timing can be astonishingly precise. Some pulsars rotate many times in a single second. Their speed comes from the collapse of a rotating star. As the core shrinks dramatically, it spins faster for the same reason a skater speeds up when pulling in her arms. A pulsar proves that the universe can produce timing more accurate than many human-made devices using an object only about city-sized.
Cosmic lighthouses and clocks born from stellar death. And speaking of ghostly particles, neutrinos pass through us all the time, completely unnoticed.
Neutrinos pass through your body by the trillions each second, right now. These particles are produced by the sun, exploding stars, nuclear reactions, and other high-energy events. They are incredibly hard to stop because they barely interact with ordinary matter. Most pass through Earth as if the entire planet were almost transparent. To detect them, scientists build enormous instruments deep underground or under ice. A neutrino can travel through a light year of lead with a good chance of getting through. They carry information from places light cannot easily escape, including the hearts of stars. Neutrinos are like nearly silent messengers from violent processes.
Silent messengers reminding us that the universe is constantly passing through us. This also relates to dark matter, something unseen yet fundamental to the cosmos.
Dark matter outweighs normal matter across the entire universe, and no telescope has ever seen it directly. Stars, planets, gas, dust, and people are made of ordinary matter. Yet when astronomers study galaxies, they find that visible material cannot explain the motions they observe. Stars orbit too quickly in the outer regions of galaxies. Galaxy clusters hold together more strongly than their visible mass should allow. These clues point to something invisible that has gravity but doesn't shine, absorb, or reflect light in the usual way. It's not dark because it's black. It's dark because it doesn't interact with light enough for telescopes to see directly. Most matter in the cosmos may be of a kind that passes through ordinary matter almost unnoticed, shaping galaxies from behind the scenes.
The unseen architect of galaxies, a truly profound mystery. And then there's dark energy, pushing everything apart.
Dark energy appears to push the universe apart faster and faster, and this discovery caught everyone off guard. In the late 1990s, astronomers studying distant exploding stars found something unexpected. The expansion of the universe was not slowing under gravity as many had assumed, it was speeding up. The name given to the unknown cause is dark energy. This doesn't mean scientists understand exactly what it is. It's a label for whatever drives the accelerated expansion. One possibility is that empty space itself has an energy that doesn't dilute as the universe grows. If so, more space means more of this effect and distant galaxies are carried away from each other ever faster. The universe isn't just expanding after an ancient beginning. Something appears to be affecting the pace of that expansion today.
An unexpected cosmic push, fundamentally changing the universe's future. It makes you wonder about the limits of what we can even observe.
The observable universe is not the whole universe, not even close. There's a limit to how far we can see, not because telescopes are too weak, but because light has had only a finite time to travel since the early universe became transparent. The observable universe is the region from which light has had time to reach us. Beyond that boundary, there may be far more universe that is simply outside our current view. It could also be larger than we can comfortably imagine. The edge of the observable universe isn't a wall in space. It's a horizon set by time, light, and cosmic expansion. What we can study may be only the visible portion of a far larger reality.
So, our perception of the universe is fundamentally limited by time, and we can even see leftover heat from that early universe, can't we?
Cosmic background radiation is leftover heat from the early universe, still reaching us today. Look far enough in every direction with microwave-sensitive instruments, and space glows with a faint afterglow. This radiation comes from a time when the universe cooled enough for light to travel freely through space. Before that, the cosmos was a hot, dense plasma that scattered light constantly. When atoms finally formed, light was released and began stretching with the expansion of the universe. Today, it arrives as cold microwave radiation from all directions. It's not coming from stars or galaxies. It's a relic of the young universe itself. Tiny variations in its temperature reveal the seeds of later cosmic structure. This background glow is one of the strongest pieces of evidence for the universe's hot beginning.
The sky is an ancient record, a direct connection to the universe's childhood. And before the first stars, there was a cosmic dark age.
The first atoms formed long before the first stars ever lit up. For a long early period, the universe was too hot for atoms to hold together. Electrons couldn't settle around nuclei because energetic light kept knocking them loose. As the universe expanded, it cooled. Eventually, electrons joined with nuclei to form mostly hydrogen and helium atoms. This happened before stars existed, which means the cosmos had a dark age. There was matter, gravity, and radiation, but no starlight yet filling the darkness. The formation of atoms was a crucial turning point because it allowed light to travel freely and matter to gather in new ways. Before the first star shone, atoms had to make the darkness possible.
So without those first atoms, stars and galaxies couldn't have formed. And then these new elements needed violent cosmic events to exist.
Every element heavier than helium needed violent cosmic events to exist. The early universe made mostly hydrogen and helium. The rest of the periodic table needed later cosmic processes. Stars fuse light elements into heavier ones during their lives. Massive stars build elements in layers, and some elements are released when stars shed material. Others require explosive deaths where extreme temperatures and pressures drive rapid nuclear reactions. The heaviest elements often need even more dramatic events, such as neutron star collisions. The universe began chemically simple, then became rich through fire, collapse, and collision. Every complex material on Earth exists because the cosmos learned to make heavier atoms over time.
The periodic table is a record of astrophysical history. And even something like gold, which we value so highly, has an origin in these extreme events.
Gold may come from colliding neutron stars, and the ring on your finger might be proof. For a long time, scientists knew that heavy elements needed extreme conditions, but the exact cosmic source of much gold remained uncertain. Then, astronomers observed a neutron star merger. The event produced gravitational waves and a burst of light that showed signs of heavy element creation. In such collisions, neutron-rich matter is thrown into space. Atomic nuclei rapidly capture neutrons, then decay into heavy elements, including gold and platinum. This process can create amounts of precious metal far beyond anything found on Earth. The gold in a ring or circuit board may have begun in one of the most violent events in the universe.
It's incredible to think that a piece of jewelry connects us to the collision of dead stars. And returning to black holes, the popular image of them as cosmic vacuum cleaners is largely inaccurate, isn't it?
A black hole is not a cosmic vacuum cleaner, no matter what the movies show you. A black hole does not suck in everything around it simply because it exists. From far away, its gravity behaves like the gravity of any object with the same mass. If the sun could somehow become a black hole without changing mass, Earth wouldn't be pulled straight inward. It would keep orbiting because the gravitational pull at our distance would be essentially the same. What makes a black hole extreme is how much mass is packed inside a very small region. Get too close, and there's no safe path back out. Stay far enough away, and ordinary orbital physics still matters. They can feed on nearby gas and stars under the right conditions, but they don't automatically consume galaxies. Their power comes from compactness, not endless reach.
That busts a major movie myth. But if one were to fall into a black hole, time itself would appear strange.
Falling into a black hole would make time look strange, depending entirely on who's watching. To someone falling inward, the trip could feel finite and terrifyingly direct. To a distant observer, the view is very different. Light from the falling object would take longer and longer to escape as it neared the event horizon. The object would appear to slow, dim, and redden, never quite seeming to cross the boundary in ordinary view. This means different observers slice time in different ways around extreme gravity. A fall into one is also a journey into the limits of how time can be compared.
It's not just trapping matter, but warping the very relationship between events and observation. And what about Hawking radiation, the idea that black holes can slowly lose energy, even though nothing is supposed to escape them?
Classically, nothing escapes from inside a black hole's event horizon, but quantum theory adds a strange twist. Stephen Hawking showed that black holes should emit a faint form of radiation because of effects near the horizon. This radiation carries energy away, so a black hole can gradually lose mass. For large black holes, the process is incredibly slow. Stellar mass black holes would take far longer than the current age of the universe to evaporate. The idea links gravity, quantum physics, and thermodynamics in one of the deepest puzzles in science. It suggests black holes have temperatures and entropy, which makes them less like simple holes and more like physical systems with hidden information.
So even darkness may not be completely final. And it's not just distant black holes, our own galaxy has one.
The Milky Way contains a giant black hole at its very center. At the heart of our galaxy sits Sagittarius A, a compact object with the mass of millions of suns. Astronomers confirmed its nature by tracking stars that orbit incredibly close to the galactic center. Those stars move around an unseen object so massive and compact that a supermassive black hole is the best explanation. The black hole isn't currently feeding as violently as those in some active galaxies, which is fortunate for our view from Earth. This discovery changes the way we imagine the Milky Way. Our galaxy isn't just a broad band of stars across the night sky. It has a dark central anchor, and millions of stellar paths are influenced by the mass hidden there.
Our galaxy's central anchor, influencing everything around it. And on that note, our galaxy, and we along with it, are moving at astonishing speed, even if we don't perceive it.
The Milky Way isn't standing still in a cosmic background. It rotates, moves within the local group of galaxies, and travels along with larger cosmic flows. Our Sun orbits the galactic center at a tremendous speed. The galaxy itself is also moving relative to the afterglow of the early universe. This motion can be detected because that background radiation looks slightly warmer in one direction and slightly cooler in the opposite direction. It's like feeling a cosmic headwind through temperature. Space may look calm on human timescales, but everything is in motion. We are riding a planet around a star inside a galaxy through a universe where stillness is almost never the default.
It's humbling to think that even when we feel perfectly still, we're hurtling through space. And when galaxies collide, it's not the violent smash-up we might imagine from movies, is it?
Galaxies can collide without most stars actually touching each other. When two galaxies meet, the event sounds like a universe-sized crash. In reality, the stars inside them are separated by such vast distances that direct collisions between stars are extremely unlikely. The real drama happens through gravity. Each galaxy pulls on the other, stretching long streams of stars and stirring huge clouds of gas. Those gas clouds can slam together, compress, and trigger bursts of new star formation. Our own Milky Way is expected to merge with the Andromeda Galaxy in the far future. This is cosmic violence without the kind of impact we imagine from everyday life. Gravity alone can remake the structure.
It's a dance of gravity rather than a demolition derby, and the universe itself is expanding faster than light in some distant regions, which seems to contradict the cosmic speed limit.
That's not the loophole it sounds like. The speed limit of light applies to things moving through space, but space itself can expand. That distinction is crucial. Very distant galaxies can recede from us faster than light because the space between us and them is stretching. They aren't locally racing through their own neighborhoods faster than physics allows. Instead, every large stretch of space between here and there adds to the total separation. This is why some regions of the universe may be forever beyond our reach. Light they emit now may never arrive because the space it must cross grows too quickly. The universe can obey its speed limit locally while still carrying distant regions away beyond light's ability to catch up.
It's a subtle but vital distinction. It means that while nothing can travel faster than light within space, space itself has its own rules of expansion. And you mentioned nothing with mass can reach light speed. Does that apply even if we had limitless fuel?
Nothing with mass can ever reach light speed, not with any amount of fuel. As something with mass moves faster, its energy increases in a way that makes further acceleration harder. Near light speed, adding enormous energy produces a tiny increase in speed. Reaching the limit would require infinite energy, which no engine can supply. This is why particles in accelerators can get incredibly close to light speed without ever matching it. For massless particles, the situation is different. Light exists at light speed. The rule is not a weakness of current technology. It is a statement about the structure of motion itself. The universe allows massive things to approach the limit forever, but it never lets them arrive.
It's an absolute boundary woven into reality. And related to light, there's a really mind-bending idea that light has no rest frame.
For almost anything else, you can imagine moving alongside it and matching its speed. But light is different. There is no valid point of view in ordinary relativity where a beam of light sits still beside you. Every observer who measures light in a vacuum gets the same speed no matter how they are moving. That fact is deeply strange because it forces space and time to adjust around it. Distances and time intervals cannot remain absolute if everyone must agree on light speed. This is one of the foundations of special relativity. It means light isn't just another fast thing traveling through the universe. It plays a special role in defining how events can be connected. The absence of a rest frame for light tells us that our everyday ideas of chasing, catching, and standing still break down at the deepest level.
That's truly counterintuitive. And the idea that moving clocks tick slower than stationary ones has been proven too, hasn't it?
Yes, this effect is called time dilation, and it's been proven again and again. If a clock moves very fast relative to you, you measure it ticking more slowly than a clock at rest beside you. The effect is tiny at ordinary speeds, which is why we never notice it while walking or driving. But at speeds close to light speed, it becomes dramatic. Unstable particles created high in Earth's atmosphere provide a natural example. Some should decay before reaching the ground, yet many survive because their internal clocks run slower from our perspective while they rush toward Earth. Particle accelerators confirm the same rule with precise measurements. Time isn't a fixed background shared by all motion. It depends on the path taken through space-time.
So a fast journey doesn't merely cover distance, it changes how much time passes for the traveler. And speaking of how motion affects objects, fast-moving objects also appear shorter.
Fast-moving objects become shorter in their direction of travel, and only in that one direction. If a spaceship could race past you near light speed, you would measure it as shortened along its motion. Its height and width wouldn't shrink in the same way. The ship's crew wouldn't feel compressed because inside their own frame, everything aboard seems normal. The shortening appears when different observers compare measurements of space and time. It's called length contraction. The faster an object moves relative to an observer, the stronger the contraction becomes. At everyday speeds, the change is too small to matter. Near light speed, it becomes impossible to ignore. Physics says length is not quite so simple. It depends on motion, measurement, and the observer's frame of reference.
It's astonishing how our perception of fundamental properties like length and time is relative to our motion. And this all comes back to Einstein's famous equation, E equals mc squared.
Energy and mass are two forms of the exact same thing. Einstein's famous equation is often treated like a slogan, but its meaning is astonishing. Mass is not merely stuff, and energy is not merely activity. They are linked aspects of the same physical reality. A system can gain mass when energy is added to it. It can lose mass when energy leaves. This connection explains why nuclear reactions release so much power compared with chemical reactions. In a nuclear process, tiny changes in mass can become large amounts of energy. The idea also works in reverse. Enough energy can create particles with mass under the right conditions. The boundary between matter and energy is not as firm as everyday experience suggests.
So, a tiny amount of mass can unleash immense energy. It's the ultimate conversion rate.
Nuclear reactions feel powerful because the conversion rate between mass and energy is extreme. The speed of light appears in the equation as a huge multiplier. That means even a very small mass difference can correspond to a vast energy release. In the sun, a little mass is lost when hydrogen nuclei combine to form helium. That missing mass becomes the energy that eventually leaves as sunlight. On Earth, nuclear power plants use fission where heavy atomic nuclei split and release energy from changes in nuclear binding. The tail lies in the scale. A barely noticeable amount of mass can become enough energy to power cities or illuminate worlds.
The power stored within atomic nuclei is truly humbling, and atomic clocks are so precise they can even measure height differences through time itself.
Modern atomic clocks are so precise that they can detect tiny changes in the rate of time between two different heights. Place one clock slightly higher than another, and the higher clock ticks a little faster because it sits in a slightly weaker gravitational field. The difference is incredibly small, but the best clocks can measure it. This turns time into a tool for sensing gravity and height. Scientists can use clock comparisons to study changes in Earth's shape, underground mass, and even the movement of water. It's a remarkable reversal of ordinary thinking. Physics allows time itself to reveal position in a gravitational field. The pace of time changes across the world we stand on.
Time itself becomes a ruler. That's an elegant demonstration of relativity. And the famous twin paradox is also real, isn't it?
The twin paradox is real enough to test with precision. Imagine one twin stays on Earth while the other travels through space at very high speed and returns. Relativity says the traveling twin can come back younger. This sounds like a contradiction because each twin might think the other was moving. The solution is that their journeys are not symmetrical. The traveler changes direction, accelerates, and follows a different path through space-time. Experiments with atomic clocks on airplanes and satellites have confirmed the underlying effect. Clocks that take different routes through speed and gravity do not always reunite with the same amount of elapsed time. It's a warning that time is more like a distance through space-time than a universal flow. Two people can separate, reunite, and honestly disagree about how much time passed along their own paths.
It truly challenges our intuitive sense of time as a universal constant. And in the quantum world, measurement itself can actually change what exists.
In the quantum world, measurement is not always passive observation. Before measurement, a system can be described as a range of possible outcomes. After measurement, one result is found. This doesn't mean a human mind magically creates reality. It means that interacting with a quantum system can change the state being measured. A delicate particle can be disturbed by the very process used to learn about it. The famous uncertainty principle reflects this limit. The more precisely certain properties are known, the less precisely other paired properties can be known. Quantum measurement is one reason the microscopic world refuses to behave like a tiny version of everyday objects. Sometimes the act of checking is part of how the answer becomes definite. Nature at small scales does not simply reveal pre-written facts. It forces us to rethink what a fact is.
So the very act of observation becomes an active participant in reality. That's a fundamental shift from classical physics, and even our understanding of the atom has evolved beyond simple diagrams, hasn't it?
An electron does not orbit like a tiny planet, no matter what your old textbook diagrams showed. That picture is useful for a first glimpse, but it's not what modern physics says. An electron in an atom is described by a quantum state, which gives probabilities for where it might be found. These regions are called orbitals, but they are not little tracks. The electron does not follow a neat path that could be filmed with a tiny camera. Its behavior is wave-like, and its allowed states depend on energy and the rules of quantum mechanics. This is why atoms emit and absorb light at specific colors. The electron changes between allowed states rather than sliding smoothly through every possibility. An atom is not a miniature solar system. It is a quantum structure with patterns, probabilities, and strict energy steps.
It's a much more nuanced and probabilistic picture of matter, and all of this atomic structure is held together by invisible electric forces.
Atoms are held together by invisible electric forces, all around you, all the time. The nucleus of an atom is positively charged, while electrons carry negative charge. Opposite charges attract, and that attraction helps bind the electrons to atoms. Without electric forces, ordinary matter wouldn't have the structure we know. Every solid object, liquid drop, and living cell depends on charged particles interacting. Yet the atom does not collapse simply because electrons are attracted to the nucleus. Quantum rules determine the allowed states electrons can occupy, which gives atoms their size and stability. This balance between electric attraction and quantum structure is why matter can persist. The invisible electric force reaches into every familiar object.
So chemistry itself works because electrons obey quantum rules, dictating how atoms interact.
Every chemical reaction depends on what electrons are allowed to do. Atoms bond because their electrons can settle into arrangements that lower energy. They react because some arrangements are more stable than others. The periodic table is really a map of electron structure. Elements in the same column behave similarly because their outer electrons are arranged in related ways. The quantum rules determine which energy levels exist and how many electrons can fit into them. They also shape the geometry of molecules, which affects everything from smell to medicine. Chemistry may look like mixing powders and liquids, but underneath it is quantum physics deciding which structures can form and which transformations can happen.
It's a quantum dance determining the very nature of substances. And there's a quiet rule about electrons that shapes everything solid.
Two identical electrons can never share the same quantum state. This rule, called the Pauli exclusion principle, quietly shapes the material world. If electrons could all pile into the same lowest energy state, atoms wouldn't build the rich structures we see. Instead, electrons must occupy different allowed states. This creates the layered electron arrangements behind the periodic table. It also gives matter much of its resistance to being squeezed. When particles are forced close together, the exclusion principle prevents identical electrons from collapsing into the same state. This pressure helps support white dwarf stars. The rule reaches from chemistry to astrophysics. Without it, the universe would be far less interesting and perhaps unable to build complex forms at all.
A fundamental principle about identical particles that allows for all the diversity and structure we see in matter. Let's look at some more common technologies that use these principles. Lasers, for example.
Lasers work because light waves march in perfect step. Ordinary light from a bulb is a jumble of many waves going in many directions. A laser is different. Its light is coherent, which means the waves are organized so their peaks and troughs line up in a controlled way. To make this happen, atoms or molecules in the laser material are energized, then encouraged to release photons that match other photons already present. The process is called stimulated emission. The result is a beam that can stay narrow over long distances and concentrate energy with great precision. This is why lasers can scan groceries, read discs, cut metal, measure distance, and guide delicate medical procedures. It turns a quantum effect inside atoms into a beam that can reach across a room or help probe the moon.
So, highly organized light from a quantum effect. What about a microwave oven? It's another common technology that uses invisible waves.
A microwave oven heats water molecules by flipping their orientation over and over. Microwaves are electromagnetic waves, and they interact strongly with polar molecules like water. A water molecule has an uneven charge distribution, so it tends to rotate when an electric field changes direction. Inside a microwave oven, the field oscillates rapidly, and many water molecules try to keep turning with it. Their motion transfers energy into the food as heat. The oven is not cooking from the inside out in a simple way, despite the common phrase. Microwaves penetrate some distance into food, then heat spreads by conduction. The everyday appliance is a physics demonstration hiding in the kitchen. It uses invisible electromagnetic waves to make molecules move more vigorously, and that microscopic motion becomes the warmth you feel when the food is ready.
So it's not internal cooking, but molecular agitation, and cameras can even see heat that's invisible to us.
Infrared cameras see heat instead of visible light, revealing a world your eyes miss entirely. Human eyes detect only a narrow slice of the electromagnetic spectrum. Warm objects also emit infrared radiation, which our eyes cannot see. Infrared cameras translate that radiation into images we can understand. A person, a warm animal, a running engine, and a poorly insulated building can stand out because they release heat differently from their surroundings. The camera is not seeing heat as a substance. It is detecting radiation linked to temperature. This makes invisible information visible. Firefighters use thermal imaging to find people through smoke. A room can be black in visible light while glowing in infrared. With the right detector, warmth becomes a picture.
It's an amazing way to perceive a hidden dimension of reality, and even X-rays, which are part of the same electromagnetic spectrum, reveal different things.
X-rays pass through soft tissue more easily than they pass through bone. An X-ray image works because different materials absorb high-energy radiation differently. Soft tissues allow more X-rays to pass through. Bones absorb more because they contain denser material with heavier atoms, especially calcium. A detector captures the pattern that remains after the radiation passes through the body. The result is a shadow picture of internal structure. This changed medicine because doctors could see fractures and other hidden problems without cutting the body open. The physics is not only about penetration, it is about contrast. The beam interacts more strongly with some tissues than others, and the detector turns that difference into an image.
So an X-ray doesn't show the body like a camera sees a face, but reveals how invisible radiation is filtered by the matter it crosses. And you mentioned the electromagnetic spectrum, meaning radio waves and visible light are fundamentally the same.
Radio waves and visible light are actually the exact same kind of thing. A radio broadcast and a beam of red light seem completely different in daily life. Physics says they are both electromagnetic waves. The difference is wavelength and frequency. Radio waves have much longer wavelengths than visible light, which is why they can bend around obstacles and travel great distances in useful ways. Visible light fits the range our eyes evolved to detect. Beyond those are microwaves, infrared, ultraviolet, X-rays, and gamma rays. They all belong to the same family. This makes the electromagnetic spectrum one of the most unifying ideas in physics. A phone signal, a rainbow, a heat lamp, and a hospital scan are not separate kinds of magic. They are variations of one phenomenon. Change the wavelength, and the same basic thing can become communication, color, warmth, or imaging.
It truly unifies so many phenomena we experience daily. And color itself isn't an inherent property of objects, but rather our brain's interpretation.
Color is your brain interpreting different light wavelengths, not a property sitting inside objects. There's no red object sending redness into your mind as a little package. An object absorbs some wavelengths of light and reflects others. Cells in your eyes respond to parts of the visible spectrum. Then your brain builds the experience we call color. This is why color depends on lighting, vision, and context. A white shirt can look different under sunlight and under a strange indoor bulb because the light falling on it has changed. Color is real as an experience, but it is not a simple property sitting alone inside objects. It is a relationship between light, matter, eyes, and brain.
Physics starts the story with wavelength, and biology finishes it by turning those signals into the vivid world we experience. What about mirrors? They seem to flip left and right.
A mirror reverses depth, not left and right, whatever it looks like at first. It feels as if a mirror swaps left and right, but that is not quite what happens. A mirror reverses the direction perpendicular to its surface. The front-back direction is flipped. Your face appears behind the glass because light rays bounce in a way that creates a virtual image at an equal distance beyond the mirror. Left and right may seem switched because you imagine turning yourself around to match the reflection. If you raise your right hand, the hand on the same side of the mirror image rises. The confusion comes from comparing your body to a person facing you. The mirror itself does not know left from right. It follows a simple reflection rule about angles. Every glance shows that our brains add interpretation to what light actually does.
Our brains are adding interpretation to a simple geometric effect. So mirrors don't lie. They just show us a truth about reflection and perception. And polarized sunglasses demonstrate how light has orientation.
Polarized sunglasses block light vibrating in just one direction. Light waves can vibrate in different orientations. When sunlight reflects from a flat surface like water, road, or snow, much of the reflected glare becomes polarized in a particular direction. Polarized sunglasses contain filters that block that dominant orientation. The result is reduced glare and clearer vision. This is why they are useful for driving, fishing, and bright outdoor conditions. The effect can be demonstrated by looking at certain screens or by rotating one polarizing filter in front of another. At one angle, much light passes through. Turn it far enough and the view can darken dramatically. The glasses are not simply making everything dimmer. They are selecting which light vibrations reach your eyes. A pair of sunglasses can reveal that light has orientation, not just brightness and color.
It's wave physics you can wear on your face. And speaking of light waves, soap bubbles shimmer with color because of light interference.
A soap bubble is surrounded by a very thin film. Light reflects from the outer surface and also from the inner surface. Those reflected waves meet each other. Depending on the film's thickness, some colors are strengthened while others are canceled. As the film drains and changes shape, the colors shift. That is why a bubble can ripple with blues, greens, pinks, and golds before it pops. The colors are not painted onto the soap. They are created by interference between light waves traveling along slightly different paths. Their beauty is a measurement of thickness at the scale of light's wavelength. A child watching a bubble float is seeing wave physics in motion.
Tiny changes in thickness decide which colors survive. And that same principle applies to oil slicks, right?
Oil slick colors come from waves canceling and reinforcing each other. When a thin layer of oil spreads across water, light reflects from both the top and bottom of the oil film. Those reflections overlap. Some wavelengths line up and become brighter. Others fall out of step and fade. The result is the shifting rainbow pattern often seen in a puddle after rain. The colors depend on the thickness of the oil film, which can vary from place to place. That is why the pattern looks uneven and alive. It is not the same as a normal pigment color. It comes from interference, where light waves combine differently depending on path length. The surprising lesson is that color can come from structure rather than dye. Sometimes what you see is not a material's color, but a wave pattern made visible.
So, colors can be created by geometry and wave patterns, and noise-canceling headphones use sound to erase sound, which still feels backwards to say.
Sound waves can add together, but they can also cancel each other. Noise-canceling headphones use microphones to listen to outside noise, then electronics create a matching sound wave with opposite pressure changes. When the unwanted wave and the generated wave meet, they reduce each other. This works especially well for steady low sounds like engine rumble. Sudden, sharp sounds are harder because the system has less time to respond. The headphones do not create silence by blocking every vibration physically. They use interference, turning sound against itself. It is a wonderfully direct example of wave physics becoming everyday technology. The idea sounds almost impossible at first. You add more sound, and the result can be less sound. Physics allows destruction to happen through perfect coordination rather than brute force.
That's a clever use of wave cancellation. And a violin string, when played, isn't just producing one clean note, but many patterns at once.
When a violinist draws a bow across a string, the string does not produce only one simple vibration. It supports a fundamental vibration and many higher patterns called harmonics. These extra vibrations help create the instrument's tone. The wooden body of the violin then responds, amplifies, and colors the sound before it reaches the listener. Change the finger position and the vibrating length of the string changes, which changes the pitch. Change bow pressure or speed, and the mix of harmonics changes too. This is why the same note can sound different in different hands. A single stretched string becomes a rich sound because it can vibrate in layered ways at the same time. Music turns wave behavior into emotion, but underneath the beauty is a precise conversation between motion, resonance, and material.
It's a beautiful example of physics enabling artistic expression. And speaking of vibrations, resonance can make bridges sway dangerously under repeated pushes.
A small push can have a large effect if it arrives at the right rhythm. That is resonance. Every structure has natural ways it prefers to vibrate. If repeated forces match those patterns, the motion can grow. A child on a swing shows the safe version. Each well-timed push adds energy and the swing rises higher. Bridges, buildings, and machines can respond in similar ways under wind, footsteps, or rotating equipment. Engineers must account for this when designing large structures. Resonance is powerful because it does not require a single huge shove. It can build from many smaller inputs arriving in step. The lesson is both simple and unsettling. Timing can matter as much as strength. Under the wrong rhythm, a stable structure can begin to move.
The Tacoma Narrows Bridge collapse is a chilling example of that, where wind alone can feed vibration into collapse.
In 1940, a suspension bridge in Washington state began twisting dramatically in strong wind and then collapsed. The event was filmed, and the footage became one of the most famous engineering lessons ever recorded. The bridge did not fail merely because the wind was strong. Its design allowed wind to feed energy into twisting motion. As the deck moved, airflow around it changed in a way that reinforced the motion further. The result grew until the structure could not survive. This disaster helped change how engineers think about aerodynamics in bridges. A solid bridge became part of a dynamic system, and the wind found a way to keep adding energy.
It's a powerful reminder of the forces at play in seemingly static structures. And a whip cracks because its tip actually breaks the sound barrier.
A whip does not make its sharp crack simply because the handle slaps the air. When the handle is moved correctly, a wave travels down the whip toward the tip. As the whip narrows, the moving energy is carried by less and less material, so the tip accelerates dramatically. It can exceed the speed of sound in air. The crack is a tiny sonic boom. This means a simple hand tool can produce supersonic motion without an engine. The physics depends on the whip's taper, flexibility, and timing. The sound is brief, but the mechanism is remarkable. Long before aircraft broke the sound barrier, humans had already done it with a flick of leather.
It's amazing that such an ancient tool demonstrates supersonic physics. And that also means sonic booms are a piling up of pressure waves, right?
Sonic booms happen when pressure waves pile together into one shock. A moving object usually sends pressure disturbances ahead through the air. At ordinary speeds, those disturbances spread away before the object arrives. Near the speed of sound, the object begins to catch up with its own waves. Once it passes that speed, the waves cannot move ahead fast enough to warn the air. They stack into a shock wave that trails behind the object in a cone shape. When that cone crosses your location, you hear the boom. It is not a single noise, made only at the moment the aircraft breaks the sound barrier. It can follow the aircraft along its path, reaching different listeners at different times. A jet does not merely move through the atmosphere. At high enough speed, it forces the atmosphere to rearrange itself violently.
It's the sound of the atmosphere violently rearranging itself. And speaking of flight, airplanes fly because wings redirect air downward, which is different from the common myth.
A wing is not simply held up by air sliding faster over the top. That idea is only part of a larger story. A flying aircraft supports its weight by pushing air downward. The air pushes back upward on the wing, and that upward force is lift. Wing shape, angle, speed, and airflow all matter. Tilt the wings slightly into the oncoming air, and it changes the direction of the flow. The pressure around the wing adjusts as the air speeds up, slows down, and bends. This creates a force large enough to hold a heavy machine in the sky. The engines do not lift the plane directly. They provide forward motion, which lets the wings keep working. Physics makes it practical by turning motion through air into a controlled exchange of momentum. A plane flies by giving the air a downward shove.
It's an elegant explanation for how something so heavy can defy gravity. And the same principles of fluid dynamics are at play in something as specific as a curveball.
A curveball swerves because spinning air changes the pressure around it. When a pitcher throws a spinning baseball, the ball drags nearby air around with it. On one side, the spin works with the oncoming airflow. On the other side, it works against it. This imbalance changes the pressure around the ball and creates a sideways force. The result is the curve that can fool a batter even when they know it's coming. The ball is not changing direction because it has a hidden engine. It is being pushed by the air it disturbs. What looks like athletic magic is a moving physics lesson delivered too fast for the eye to fully unpack.
So, controlling invisible fluid motion is the key to athletic skill. Returning to water, boiling water actually cools itself, doesn't it?
Boiling water cools itself because the fastest molecules leave first. At the surface of hot water, some molecules are moving faster than others. The fastest ones have enough energy to break away into vapor. When they escape, they carry energy with them, leaving the remaining liquid with a lower average energy. That is cooling through evaporation. It is the same reason sweat helps cool your skin. The water molecules that leave your body take heat away as they enter the air. Boiling intensifies this process because bubbles of vapor form within the liquid and rise out. The key is that temperature is an average, not a promise that every molecule has the same energy. A pot of water contains a crowd of particles with different speeds. The quickest are the first to leave. That makes boiling a sorting process where the most energetic molecules escape and the liquid they leave behind can cool.
It's a microscopic sorting process happening constantly, and steam burns badly because it releases hidden heat.
Steam at boiling temperature can injure skin more severely than liquid water at the same temperature. The reason is phase change. When water becomes steam, it absorbs a large amount of energy without changing temperature. That stored energy is called latent heat. When steam touches cooler skin, it condenses back into liquid water and releases that energy directly onto the tissue. Then the newly formed hot water can continue transferring heat. This double effect makes steam especially dangerous. The strange part is that a thermometer may show the same temperature for boiling water and steam, yet the steam can deliver far more energy during condensation. Physics reminds us that temperature is not the whole story. Heat depends on how much energy is transferred and how matter changes form.
A cloud from a kettle can carry a concentrated thermal surprise, and a pressure cooker uses this understanding of pressure and boiling point to cook faster.
A pressure cooker raises water's boiling temperature above normal. In an open pot, water boils when its vapor pressure matches the pressure of the air above it. A pressure cooker traps steam, which increases the pressure inside the sealed vessel. Under higher pressure, water must become hotter before it can boil. That hotter water cooks food faster because heat moves into ingredients more aggressively. The cooker is not using a mysterious cooking force. It is changing the boiling point by changing the surrounding pressure. The sealed environment also keeps more moisture inside, which helps transfer heat through steam and liquid together. This is everyday thermodynamics with a locking lid.
It's a simple pot changing the temperature range water can reach, and something like touching metal where it feels colder is also about heat transfer.
Metals feel colder because they carry heat away from your skin faster. Touch a metal spoon and a wooden table in the same room. The metal usually feels colder even though both objects may be at the same temperature. Your skin is not measuring temperature directly. It is sensing how quickly heat leaves your body. Metal conducts heat well, so it pulls energy from your skin rapidly. Wood conducts poorly, so heat leaves more slowly, and it feels warmer. This is why a tile floor can feel cold on bare feet, while a rug beside it feels comfortable even in the same room. Coldness is often the speed of losing heat.
So sensation is about heat flow, not just the object's temperature, and fire itself isn't a solid thing.
Fire is glowing gas and particles releasing energy, not a solid thing at all. A flame is not a solid object, even though it has a shape you can point to. It is a region where chemical reactions are happening fast enough to produce heat and light. Fuel molecules break apart and combine with oxygen, forming new substances while releasing energy. That energy heats nearby gas and tiny particles until they glow. The blue part of the flame often marks more complete combustion. The yellow glow can come from hot soot particles radiating light before they burn away. A flame keeps its shape because hot gases rise and fresh oxygen flows in. Remove heat, fuel, or oxygen, and the reaction stops. Fire feels ancient and familiar, but it is a dynamic process rather than a thing. It is matter changing partners at high speed, with released energy becoming warmth, motion, and light. A candle flame is chemistry made visible through physics.
It's matter transforming at high speed rather than a solid object. And fluorescent materials show us how invisible light can become visible light.
Some materials can take in light at one wavelength and emit light at a longer wavelength. Under ultraviolet light, they may glow in colors that seem to appear from nowhere. The incoming light gives electrons in the material extra energy. When those electrons drop back down, they release some of that energy as visible light. The emitted light has lower energy than the absorbed light, which is why invisible ultraviolet can become a bright, visible glow. This effect appears in highlighter ink, security markings, minerals, and biological imaging. Fluorescence is not the same as reflection. A fluorescent object is not merely bouncing light back. It is absorbing energy, briefly storing it in electronic states, and sending part of it out again in a new form. The glow is a tiny energy conversion event repeated by countless molecules.
So it's an energy conversion happening at the molecular level. And some materials have a kind of memory.
Shape memory materials can return to a previous form when heated or triggered in another way. The most famous examples include certain metal alloys, such as nickel titanium. Bend the wire made from one of these alloys, then warm it, and it can spring back to a programmed shape. The effect comes from changes in the material's internal crystal structure. At lower temperatures, one structure can be deformed more easily. When heated, the atoms shift into another arrangement that restores the original form. This is not memory like a brain stores a picture. It is memory built into atomic geometry. These materials are used in medical devices, eyeglass frames, actuators, and clever mechanical systems. The fascination is that a solid object can appear to remember what it used to be. Heat unlocks a hidden instruction written into the way its atoms prefer to arrange themselves.
Atomic geometry remembering its past. That's a unique property. And then there are non-Newtonian fluids that can harden suddenly when struck.
Some fluids refuse to behave like ordinary liquids. A shear thickening fluid can flow when handled slowly, then stiffen when hit or squeezed quickly. The particles inside it are suspended in liquid, and under sudden stress, they jam together. The material becomes temporarily harder because the particles cannot move past one another easily. When the stress is removed, it can loosen again. This makes the behavior feel almost alive, even though it is just physics. Researchers study these materials for protective gear, flexible armor, and impact-absorbing systems. The appeal is obvious: a material that stays soft during normal motion, but stiffens during a blow. The key is that its response depends on how force is applied over time. Push gently, and they yield. Strike quickly, and they resist.
It's like having a material that instantly adapts its properties to the force applied. And cornstarch and water are a common example of this, aren't they?
Mix cornstarch with water and you get a strange substance, often called oblek. Move your fingers through it slowly, and it flows like a thick liquid. Punch it or slap it, and it can feel solid for an instant. The grains of starch are packed in water, and sudden force can make them jam together. The water cannot move out of the way fast enough, so the particles lock into a temporary structure. This is why people can run across a pool of the mixture if they keep moving fast, but sink if they stop. It is a perfect hands-on physics experiment because the effect is immediate. A bowl of kitchen ingredients becomes a lesson in how matter can switch behavior when stress arrives too quickly.
It's a fun way to experience how matter can have properties in between liquids and solids. And speaking of granular materials, sand dunes can actually sing.
In certain deserts, a sliding dune can produce a deep humming sound that carries across the landscape. The effect happens only under special conditions. The sand grains must have the right size, shape, dryness, and surface coating. When a layer of grains avalanches down the dune, many grains move in a synchronized way. Their collisions create vibrations that the dune can amplify. The result can sound like a low musical note or distant engine. Not all dunes do this, and even a singing dune may stay silent when the sand is damp or disturbed. The phenomenon shows that a landscape can behave like an enormous natural instrument. The sound is not coming from wind alone. It is produced by countless grains moving together with unexpected order. A dune may look still for days, then suddenly reveal that its surface can turn motion into a voice.
That's a surprising sound from a seemingly inert landscape. And on a smaller scale, Static electricity can make our hair repel itself.
Rub a balloon on hair and electrons can move from one surface to another. This gives the hairs the same type of electric charge. Like charges repel, so the strands push away from each other and stand outward. The effect looks playful, but it reveals a basic rule of electricity. Matter may usually seem neutral, yet tiny charge imbalances can create visible forces. Dry air makes static effects stronger because charge has fewer easy paths to leak away. Static electricity is electricity out of balance. It can lift hair, cling clothes together, and make dust stick to surfaces. The forces are small, but they are direct evidence that invisible charge can push and pull ordinary objects.
Invisible charge creating visible forces, and a balloon sticking to a wall also involves this shift in electric charges.
After a balloon is rubbed on fabric or hair, it can gain extra electric charge. Bring it near a neutral wall and the charges inside the wall respond. Opposite charges shift slightly closer to the balloon, while like charges shift slightly farther away. The wall as a whole remains neutral, but the near side becomes more attracted than the far side is repelled. That tiny imbalance can hold the balloon in place. Nothing sticky has been added. The balloon is clinging through electrostatic attraction. This effect is called polarization, and it happens because charges in matter can rearrange a little under an electric influence. It shows why neutrality is not the same as being unaffected.
Even a neutral object responds strongly when its internal charges are nudged. And speaking of electrical phenomena, lightning begins with charge separation inside storm clouds.
Inside a storm, rising and falling air throws ice crystals, droplets, and soft hail into constant collisions. Those collisions help separate electric charge within the cloud. One region becomes more negatively charged, while another becomes more positive. The exact details are complex, but the result is a growing electric field. The air normally resists electrical flow, yet a strong enough field can break that resistance. At that point, the atmosphere becomes a path for a sudden discharge. The ground beneath the storm also responds because charges there shift under the influence of the cloud. What looks like one bright flash begins as a huge hidden imbalance built by turbulent weather. A thunderstorm is therefore not only a rain machine, it is a charge sorting system with moving ice, violent air currents, and enormous stored electrical energy. Lightning is the moment that imbalance finds a way to release itself.
A storm is an immense electrical machine, and the Earth itself acts like a giant magnet.
Our planet has a magnetic field that reaches far into space. It is not produced by a bar magnet hidden inside Earth. The field comes from motion in the planet's outer core, where electrically conducting liquid metal moves under the influence of heat, rotation, and convection. This moving metal generates electric currents, and those currents produce magnetism. The field is not perfectly steady. It shifts, wanders, weakens, strengthens, and has reversed direction many times in Earth's history. Its presence matters because it helps guide charged particles from space and shapes a protective region around the planet. Without it, the upper atmosphere would be more exposed to the solar wind. The magnetic field is invisible, yet it is one of Earth's great active systems. Beneath our feet, deep metal motion helps create a shield that extends far above our heads.
The ground is part of a planet-sized electromagnetic engine, and compasses work because of this molten metal moving beneath our feet.
A compass needle aligns with Earth's magnetic field, which is why it can point roughly north. That field is generated deep below the crust, not at the surface. In the outer core, liquid iron-rich material moves as Earth loses heat from its interior. Because the material conducts electricity, its motion helps sustain the geodynamo. The compass needle responds to the magnetic field produced by that deep process. It does not point exactly to the geographic North Pole. It points toward magnetic north, which drifts over time. The simple needle in a compass is therefore connected to a churning layer thousands of kilometers below. Holding one in your hand links you to Earth's interior. A small pivoting magnet becomes a surface instrument for a hidden planetary machine.
It's a direct connection to Earth's deep, dynamic core, and this magnetic field also creates the auroras.
Auroras happen when solar particles strike Earth's atmosphere, painting the sky as they go. The sun releases streams of charged particles into space. When those particles reach Earth, many are guided by the planet's magnetic field toward polar regions. There, they collide with atoms and molecules high in the atmosphere. Those atmospheric particles gain energy, then release it as light. Oxygen can glow green or red, while nitrogen can produce purple, blue, or pink tones. The colors depend on altitude, particle type, and energy. An aurora is not simply sunlight reflecting from the sky. It is the atmosphere being excited by space weather. During strong solar storms, auroras can spread farther from the poles and become more intense. The shimmering curtains overhead are a visible connection between Earth and the Sun. They show that our planet sits inside a changing flow of charged matter.
It's space weather painting our sky, and this charged matter brings us to plasma, which is the most common form of matter in the universe.
On Earth, solids, liquids, and gases feel like the main states of matter because they fill our daily experience. Across the universe, plasma dominates. A plasma is a gas-like state in which electrons are separated from atoms, creating a mixture of charged particles. Because it contains charges, plasma responds strongly to electric and magnetic fields. Stars are made of plasma. The glowing material in nebulae can be plasma. Lightning and auroras involve plasma too. The reason plasma is so common in space is that high temperatures and energetic radiation can strip electrons away from atoms. Once matter becomes charged, it behaves in ways an ordinary gas does not. It can flow along magnetic fields, form filaments, and produce light. Plasma reminds us that the familiar states of matter are local comforts. The wider universe is often charged, glowing, and magnetically shaped.
So the familiar states of matter are a local exception, with plasma being the cosmic rule. And the sun itself is mostly plasma, not fire in the ordinary sense.
Fire needs chemical fuel and oxygen, but the sun is not burning in that ordinary sense. Its visible surface and deeper layers are made mostly of ionized gas. Electrons and nuclei move through a hot, charged state of matter. The sun glows because energy from its interior heats this plasma until it emits intense radiation. Its surface boils with huge convection cells, while magnetic fields twist through the charged material and help produce sunspots, flares, and loops of glowing gas. Thinking of the sun as fire makes it seem like a giant campfire in space. The real object is far stranger. It is a self-gravitating sphere of plasma held together by gravity and powered from within. Its behavior depends on nuclear physics, fluid motion, radiation, and magnetism. Every sunrise is the light of a star whose surface is not flame, but a vast ocean of charged matter.
It's a vast ocean of charged matter powered by fusion, and fusion is what makes stars shine.
Fusion powers stars by joining light atomic nuclei together. In a star's core, gravity creates enormous pressure and temperature. Under those conditions, light nuclei can get close enough for the strong nuclear force to bind them together. In stars like the Sun, hydrogen nuclei ultimately form helium through a chain of reactions. The final helium nucleus has slightly less mass than the starting ingredients. The missing mass becomes energy, which slowly works outward and eventually escapes as light. Fusion is difficult because positively charged nuclei repel each other. A star succeeds by crushing matter into conditions that make rare close encounters happen constantly across a huge volume. This is why stars can shine steadily for immense spans of time. They are not using ordinary fuel. They are converting the simplest atoms into heavier ones while releasing energy from the deep binding of nuclei. Fusion is the engine that makes starlight possible and turns gravity into a cosmic power plant.
It's the ultimate cosmic power plant. And on Earth, we use fission, which splits heavy atoms to release energy.
Fission splits heavy atoms and releases the energy stored inside. Some heavy atomic nuclei are unstable enough that splitting them can release energy. In fission, a nucleus such as uranium can absorb a neutron, become disturbed, and break into smaller nuclei. Additional neutrons may fly out, and those neutrons can trigger more fissions. This chain reaction can be controlled in a reactor or released rapidly in a weapon. The energy comes from the way nuclear binding changes when a heavy nucleus becomes smaller, more tightly bound pieces. It is not chemical burning. The nucleus itself is being rearranged. Nuclear reactors use this process to heat water, produce steam, and drive turbines that generate electricity. The astonishing part is the density of energy. A small amount of nuclear fuel can release vastly more energy than the same mass of ordinary chemical fuel. Fission shows how much power can be stored inside atomic nuclei.
It's a powerful demonstration of energy stored within atomic nuclei, and radioactive decay, while predictable in large samples, is completely random for each individual atom.
A radioactive atom has no tiny clock hand showing exactly when it will decay. For one atom, the moment of decay is unpredictable. For a large collection of identical atoms, the pattern becomes reliable. Half-life describes how long it takes on average for half the atoms in a sample to decay. This combination of randomness and predictability is deeply quantum. It means scientists cannot say when a specific unstable nucleus will change, but they can forecast the behavior of enormous numbers with remarkable accuracy. The process can release particles or radiation as the nucleus moves toward a more stable state. Its strangeness lies in the scale shift. One atom behaves like a roll of the dice. A large sample behaves like a clock. Nature can be fundamentally uncertain and statistically precise at the same time.
It's that tension between individual randomness and statistical certainty that makes it so fascinating. And carbon dating relies on this predictable decay.
Carbon dating works because unstable atoms decay at predictable rates. Living things take in carbon while they are alive, including a small amount of radioactive carbon. After death, exchange with the environment mostly stops, and that radioactive carbon begins to decay without being replaced. By measuring how much remains, scientists can estimate when the organism died. The method is especially useful for once-living materials, such as wood, cloth, bone, and charcoal within a certain age range. The power of the technique comes from half-life predictability. Individual atoms decay randomly, but the average behavior of a large sample is stable enough to become a time-measuring tool. Carbon dating turns nuclear physics into a way of reading history. A fragment of ancient wood can carry a fading atomic signal, and that signal can help reveal when a fire burned or a tree was cut.
It's remarkable how nuclear physics allows us to read the history of ancient life, and particle accelerators allow us to recreate conditions from the early universe right here on Earth.
In a particle accelerator, electric fields give particles enormous energy, and magnets steer them around carefully controlled paths. When particles collide, their energy can concentrate into a tiny region for an instant. That can produce new particles and interactions similar to those that existed when the universe was much hotter and denser. These machines do not recreate the whole early universe like a miniature explosion. They recreate specific high-energy conditions on a microscopic scale. The results help test the deepest models of matter and forces. The fascination is that humans can build a machine on Earth that briefly touches regimes of nature otherwise found only in cosmic extremes. A collision lasting less than a blink can reveal rules written into the earliest moments of reality.
It's a way to explore the very beginning of everything in a laboratory, and the Higgs field gives many particles their mass.
The Higgs field is thought to fill all of space. Some elementary particles interact with it strongly, and those interactions give them mass. Others interact weakly or not at all. The Higgs boson is a particle associated with this field, and its discovery confirmed a major piece of the Standard Model. Without the Higgs mechanism, many particles wouldn't have the masses needed for atoms and ordinary matter to exist as they do. The field is not a material fog slowing particles down in the usual sense. It is a quantum field with a non-zero value even in empty space. Particles behave differently because of how they relate to it. This makes mass feel less like an obvious built-in property and more like a relationship with something everywhere. The weight of matter has roots in a field we do not directly see.
So, the very concept of mass is rooted in an invisible, ubiquitous field. And antimatter exists, but annihilates instantly with ordinary matter.
For many particles, physics allows a matching antiparticle with the same mass and opposite charge. The electron has the positron. The proton has the antiproton. When matter and antimatter meet, they can annihilate, converting their mass into energy and other particles. Antimatter is not fiction. It is produced naturally in some radioactive decays and cosmic ray interactions. It is also created in laboratories and used in medical imaging. The mystery is why the visible universe contains so much matter and so little antimatter. The early universe should have produced both in great abundance, yet something caused matter to win by a tiny margin. That small imbalance allowed stars, planets, and people to exist. Antimatter shows how symmetrical the laws of physics can be, then points to one of the biggest unsolved questions. Why is there something made of matter here instead of equal matter and antimatter vanishing into radiation?
It's a fundamental question that challenges the very existence of our universe. James, this exploration of physics has shown how deep and strange reality is, from the cosmic to the everyday. It's a journey that really connects the largest structures to the smallest events.
Physics can explain both galaxies and a single falling raindrop. The same subject reaches from the largest structures we can observe to the smallest events in daily life. It describes how galaxies gather under gravity and how a drop of rain forms, falls, flattens, and breaks apart in air. That range is what makes physics so powerful. It does not treat the universe as separate compartments of wonder. It searches for rules that connect motion, energy, matter, light, and force across every scale. A raindrop is shaped by surface tension, airflow, gravity, and collisions with other droplets. A galaxy is shaped by gravity, motion, dark matter, gas, and time. The details are different, but the ambition is the same. Physics asks what the world is doing and why it behaves that way. It can make the ordinary feel larger and the cosmic feel more understandable. Look closely enough, and even the smallest event becomes an entrance into the machinery of reality.
James, thank you for this incredible journey through the strange and surprising world of physics, revealing the hidden machinery behind everything we experience. If you found this conversation thought-provoking, consider sharing it with a friend who might also enjoy delving into these profound scientific insights.